In this video, we're going to take a look at the algorithms that we may or may not want to use in generating a color palette. In my previous blog post, we looked at how color palette generation is often lacking and misses some key points. Distinct colors that occupy a low percentage of the total image are lost. Colors isolated from their surroundings appear too dull or too bright in comparison to the original image. Ideally, our generation technique should solve these two issues. Let's take a look at how we might accomplish this. Our first step will almost certainly be to organize our data. Visually, the position of pixels in an image are critical to the information integrity. A picture of a smiley face loses its meaning even if the same pixels are randomly shifted around. Equally so, organizing the data into distinct categories does the same. Some information is lost. We can no longer see that this was ever a smiley face by simply splitting up the white and black pixels. We can, however, use this reduction to our advantage. One of the issues we were seeing when we were creating palettes is that you might have a small but frequent pocket of distinct color, here like the red. A naive palette generation technique might look at blotches of colors in an image over a certain size. As a result, you might lose some of those distinct colors that you wanted as part of your palette. Here we can see that only the yellow and green were selected for the palette because the red blotches were too small and the algorithm ignored them. By organizing our data in a way that makes the position in the original image irrelevant, we can more easily identify the colors that may have slipped by when using that more naive approach. We can even further reduce the data, but this time more conceptually. Here we can reduce the data to a simple list with properties that define those colors. Here we can see that the source image, being yellow, green, and red, have been reduced to their RGB values. This is the common color space and the one we'll probably work with going forward. Having made this second reduction, we can begin to see that there is some very simple data that we can work with when creating our algorithms and, in the end, actually programming it. This process, start to finish, is more commonly known as color quantization, or in a broader sense, just quantization. Quantization is the process of constraining an input from a continuous or otherwise large set of values, such as the real numbers, into a discrete set, such as integers. We have a large set of data, all of our pixels and their RGB values, and we want to organize them. For our purpose of color quantization, we want to organize our colors into distinct groupings that we can use as a palette. Fundamentally, quantization in this context is about converting our analog data source into a digital one. We have our original image, and we want to define it by its most distinct colors, a palette. So how are we going to quantize our color data then? As we saw previously, we just need to make a list of all the colors in the image. In fact, counting the number of occurrences, while potentially useful later on in determining how common a color is, isn't even needed for our purpose. This is where we encounter our first problem. Counting colors is easier said than done, and our first approach, while not very good, is quite simple. This simple approach is to simply look at a color in the list, check if it's already been seen, and if not, add it to the list. Very simple and very, very slow. This particular technique in big O notation is 2 to the n time complexity, which as far as time complexities go, is only outshone in poor performance by big O n factorial. Being second last just isn't going to cut it here. Especially when working on HD images, or let alone Ultra HD or 4K, we have over 2 million pixels that we need to check, and any of those pixels can be one of 16 million different colors in the RGB space. This list check technique just runs out of control very quickly and is totally infeasible. We'll need a better method. Problem 2. Can you tell these colors apart? If you spend a little bit of time staring, you can probably tell they are very slightly different. Sample B has slightly less green in it. And so arises our issue. To the computer, when we compare two colors, digitally defined by their red, green, and blue components, they are either identical or not. All 16 million colors are unique. By converting our analog image into its digital constituents, we must accept that we play by digital rules now. Any hand-created palette would lump these two colors together. We would almost certainly never allow them to occupy two different colors in our palette. By computer standards, however, they are as distinct from each other as they are from sky blue. We need some way of determining when two colors are similar and allow us to categorize them together as a single color for the final palette. So, what are the two problems we are actually looking to solve here? First, we need a way of checking our list of colors to see if we have already seen it before, while also staying within the time complexity that is below O of n. And second, we need a way of categorizing colors that are very similar together. Enter the solution, the octree. An octree is a tree data structure in which each internal node has exactly 8 children. Octrees are most often used to partition a three-dimensional space by recursively subdividing it into 8 octants. Octrees are the three-dimensional analog of quadtrees. So why is this helpful to us? The key is in the most often used to partition three-dimensional spaces part. Now, aren't we dealing with colors and not three-dimensional space? By using the RGB color space, we have essentially what amounts to a 3D coordinated system in a 256 by 256 by 256 cube. Each point in the cube corresponds with one of the 16 million colors in the RGB space. It is, however, important to note this cube is entirely virtual. It's not actually part of the data structure that we are going to implement. It is only a tool for visualization. Rather, the structure is that of a regular tree. Each branch has 8 sub-branches, and each of them 8 more, and so on. At a depth of 8 branches, you would have the precise position of the color. Two nearly identical colors, differing by only one value, would be directly adjacent to each other within this space. As the colors descend through the branches, at each of the 8 nodes, it splits off into the appropriate subpartition that it belongs to. As it goes, we can provide it a code of sorts to define its travel path. For instance, a color that travels into the 6th partition, then the 3rd partition, and then the 7th partition, and so on, would acquire a unique code that begins with 637. Within that partition, or within all of those sub-branches, you would find just over 2 million colors. 2 million colors that, by using this partition technique, are more similar to each other than the other 14 million. Do you see where this is going? In our previous example, we saw 2 yellows that were very similar. Using these 2 colors, we would only need to descend 5 branches before these 2 colors were in totally separate partitions. What we can do is group colors by branch or partition and increase or decrease the degree of difference between them simply by moving up and down the tree's structure. This move up and down through the branches and discarding the one below is called pruning. We can adjust the way we prune by using totals that are above or below that branch, and by creating some specific rules, we can solve one of our first major issues. Distinct colors that occupy a low percentage of the total image are lost. The pruning techniques we use can preserve small, isolated pockets where we may find a specific partition has high density, while the ones around it are more sparse. Additionally, the refined problem we identified of a way of categorizing similar colors together has also been solved by doing this. And while we're on a roll, the issue of a way for distinguishing if a color in an image has already been seen before has been blown out of the water with a reduction from O to the 2 of n to a tiny O of log n. So, it seems we found a reasonable algorithm to use. In summary, we're going to use a tree over a list. Not only does this render time complexity to a total non-issue, but it also reveals the spatial relationships colors have to each other, allowing us to group similar colors together. To do that, we can fine-tune our pruning weights for each level of the tree. So, what's next? Well, the next step is implementation. We'll take our research and apply it to actual code and see how it turns out. Look forward to it.